So those of you that are at home, are you looking at a white disc on a blue background right now? Yes? Okay. And those of you that are here can see it, right? So if I come over here and start manipulating this, because it's a little bit tricky when I'm holding things up to show people in class and also people on Zoom. So I'm going to use this document camera. Oh, thank you. Paul just turned off the fan. I feel like I just got my hearing back. Um, and my name's Dan Abbott. I've been teaching here my 35th year. So Paul and Meredith are both students of mine. I will have to say, probably the two best students I've ever had. And I'm sure you recognize that having had them as instructors. So, Paul asked me to do this because my background is machine tool. This is the kind of thing I do training on all the time. I do training for companies. I really like this particular field. It's a little bit esoteric, as in that not many people find it interesting. So that's one of the reasons why I get to do so much training. What I want to do, I'm sharing the screen now. So Paul, I'm going to open up the assignment sheet for this assignment.
Yeah, I didn't post. I did. I posted the module, but you can just open it up from.
Yeah, let me just go open it.
160.
So the idea, yeah, I'll go grab it off of.
Yeah, 160.
Is it in the student side right here?
Yeah, and then drawing assignments.
Drawing exercises, ASME right here. Oh, it's the PowerPoint. Mechanical Gd&T right here. So one of the reasons why we designed this CAD applications course is so you could get better at AutoCAD, but also so you get an experience with how AutoCAD gets applied in different disciplines. So this discipline is known as mechanical design. And the drawing itself comes directly from a document called the ASME, which stands for American Society of Mechanical Engineers, Y14.5 document on dimensioning. I'll show you what it looks like. And it looks like this. That's actually several versions of it, but it's several hundred pages that indicate what the standards are for creating mechanical drawings. And every manufacturer in the United States follows those standards voluntarily. And when they do, in the title block, they put a reference to the ASME standard. It's one of those things where a lot of companies think they understand the standard and often don't. And sometimes that ends up costing them a lot of money, which is one of the reasons why I get to do outside training. And I do just as much as I feel like, because I'd rather teach here than do outside training. So the drawing you're going to do is this one, but rather than have you just do it, Paul was interested in having me explain what is going on here and why all of these things appear in the way that they do. And there are some tools in AutoCAD that allow you to add the particular symbols that are being shown here. So my goal today is to tell you a little bit about something called geometric dimensioning and tolerancing. Like I said, the documentation for it, and just to scare you even more, I did one advanced class one time, and there's the advanced class manual for that. And this is in addition to the manual itself. The point I'm making here is we're going to cover the overview today. You're not going to learn everything there is to know about this, partly because I don't know everything there is to know about this. So first, you've done some mechanical things, right? Yeah. So what you've been looking at so far is dimensions, and dimensions and tolerancing are related, but they're not exactly the same thing. Dimensions have tolerances, and dimensions are size. So I've got a document here. I've got a model here, and the model is directly out of the standard, and it's a model that they use to represent how to apply the standard in different ways. So what I have, I don't know if I can do this. I've got two of these now, and they have a bolt hole pattern. A bolt hole pattern is that series of holes that goes in a circular fashion. And although they weren't designed to bolt to each other, they could bolt to each other if the surfaces are flat enough, and if the holes line up well enough, and if the holes are themselves large enough, and if the entire pattern is in the right location. Those are all geometric concerns as opposed to dimensional concerns. So if you look at this, all these numbers over here are dimensions. Dimensions always have a tolerance, which means there is nothing you do that can be exactly 44.6 millimeters. When you have a dimension on a print, what you have to do is indicate the extent of variation permitted and still have that part function as designed. Now, most of you have done building, I'm sure. And if you built yourself a deck and in the back of the house, you hired me and I came over and you said, I want to make sure when you make these cuts that every single board is cut within a 64th of an inch. I'd say, get yourself another carpenter. That tolerance is ridiculously small. I should have a little more room to miss that height or that length and still have the part work. Because if I'm off by a quarter of an inch on your deck, it's still going to hold up. The deck's still going to stand up. So in some fields, the actual tolerances aren't ever specified because the understanding is they're big enough, so you're going to get them. So carpenters never see a print that says, oh, when you cut this, plus or minus a 16th of an inch. Carpenters just build it as close as they can. And when they build it as close as they can, it's easy to do and it works because there's not a great deal. The tolerance itself is big enough for variation so it doesn't affect the function. Does that make sense? So far, so good? Well, machine tool is another matter. In machine tool, we deal with tolerances that are sometimes as small as a tenth of a thousandth of an inch. So if I had hair and I could pluck one off my head, which I don't, and then I took that hair and I split it into 30 parts, I'd be talking about a 10,000th of an inch. So we're talking here about very, very small tolerances sometimes, not always. And the concept of tolerance, no matter what your discipline, is always a balance between what you need for the part to function and how much that part costs. So one of the reasons why Rolls Royces were such good cars is because they had extremely close tolerances, and that made them extremely expensive. So would you be willing to spend the equivalent at one time of $200,000 or $300,000 in a car? If I said, yeah, but the tolerances are really close, I'd go, you know what? My Chevy's got pretty good tolerances and it's a lot cheaper. That's when I'm going to go. So the concept of tolerance is always a balance. So what you have here is this. All these are size tolerances, and a size tolerance just means you cannot go beyond 44.6 when you bore this hole. That hole is a diameter, and it can't be smaller than 44.45. Those two numbers represent the two extremes, and one of those extremes is called maximum material condition, and one of them is called least material condition. In geometric dimensioning and tolerancing, those two concepts are really critical. And it means this. That opening right there, that's a little pocket. You can see that pocket's right here. You guys see that pocket right there, right? That little pocket that goes in here. Oh, I have to switch over to this. That little pocket that goes in there right here, that has to be a certain size in order for the part to work. So if, going back to this, yeah. So if you take a look at it, one of those sizes is as small as that pocket can be. That's when the part has the maximum amount of material in it. So you think about it, when that pocket and those holes are as small as they can be, that part weighs the most it can weigh. That's the maximum material. The reason that's an important concept is that's when it's least likely to go together with the thing where it has to go together on. So I have something here that's got a little pin that sticks out, and this thing has to go over that pin. If it goes over that pin, that means that the hole itself, the pocket, is not smaller than 44.45. It might be bigger than that, and it's okay if it's bigger than that as long as it doesn't go past 44.6. So that is one way of tolerancing things. But it turns out, I'll do a little history here. In fact, can I open, hang on, I'm going to open up PowerPoint. I actually thought about writing a book on how geometric dimensioning and tolerancing won World War II. I'm going to show you why in a minute. I was at the Library of Congress and I tried to get some information about it, but it turns out I couldn't really find enough to write a book. So I just have a theory. But the, oh, do I have to, I can open a PowerPoint here, can't I? I'm logged in as Paul, so I don't know. Maybe Paul has things set up differently than I do. Oh, I just have to say yes. I really mean it. There we go. So this is the PowerPoint I use when I do training for companies. And if anybody would like it, I'd be happy to let you have it. But you can see that it deals directly with this same illustration. And that illustration, like I said, comes out of the geometric, out of the tolerance itself. But I've got a little bit of a, where did I put it? I've got a little history here. One of the reasons I do this is because I do training, people sometimes say, oh, that newfangled thing, tolerancing, geometric stuff. 1935 is when the first standard was developed for technical graphics. It didn't have any geometric controls, but the key thing here is the Royal Torpedo Factory. And the Royal Torpedo Factory was a factory in Scotland that made torpedo launching equipment for submarines. And they had a fellow who worked there who supervised the whole thing. And they were running out of parts. And so they were getting parts made from the United States, and those parts are being shipped over. But they ran out when they were assembling one of the launching mechanisms. And the people who were working overnight said, we got a bunch of rejected parts over here. Let's just see if we can make those work. So they had been rejected because they were out of tolerance, but they were out of size tolerance. That means the sizes didn't quite work. Well, they put them together, and it turns out they were actually able to make some launching devices that did work. So when the man in charge came in, he saw that they'd done that, and he was actually in a position where he could have court-martialed them, but instead he goes, I wonder why they worked. And he discovered that if you control the shapes as well as the dimensions of something, you're able to have a much better control over whether or not parts will work. So for instance, if I have that tube right there and I measure it along its length, and every time I measure it, it comes out exactly the right size, but the tube itself is bent a little bit. The tube's not straight, but it measures, everything just measures just fine. So if you wanted to slide it into something, it won't go because it's a crooked tube. Does that make sense or not? That's the straightness tolerance. Well, on the other end of this parts that did work, but looked like they wouldn't, that was a positive thing. The negative thing was a submarine that had other devices in it that met size tolerances, but did not meet what we would call now geometric tolerances. And the most successful submarine in World War II shot a torpedo at a Japanese ship that went skewing backwards and spiraled back and hit the submarine itself and sank the submarine. So what came out of both of those things was the need to define parts more accurately than just the dimensions. The dimensions themselves just weren't enough. So the geometry of the part also had to be taken into account. So if we come back here, what you're looking at here, besides the numbers, which are dimensional tolerances, are geometry tolerances. And so that box right there is called a feature control frame. And a feature control frame looks like this. And that's about as complex as one gets. Those numbers are not dimensional numbers. Those numbers all have to do with the geometry itself. The geometry is the shape, perpendicularity, parallelism, roundness, straightness. Those concepts are the things that are being controlled by that. Make sense so far? I'm seeing some nods in here, people at home. Well, I'll talk about how you measure that a little later on because it gets a little tricky sometimes. But when you have a feature control frame like this, and again, this comes directly from that standard illustration, which is the one you're going to be working from. When you have a feature control frame, it has these little components. And the first component you have, that one right there, that tells you what is the concept, the geometric concept that's being controlled. In this particular case, it's something called positional tolerance. And positional tolerance means this. If I have things that have to line up, the holes have to line up. If the hole that I put in this part is exactly the right size, but it's not in exactly the right position, and I try to take these things and match them up, and two of the holes don't line up quite, I can't put a bolt through it. So positional tolerance is what controls the location of those holes as well as the size. And not only does it control the location, but it also controls how straight the hole goes through something. So if you're looking at a hole, suppose I have a part, and that part is this thick right there. There is an axis to that hole. You can't see it. It's artificial. It's imaginary. But I'm going to pretend that the axis is this. So the axis of the hole is what determines not only the position of the hole, but also how straight the hole is. So if you have an axis, a center hole like that, if I move the axis, it moves the hole around as well. If I tilt the axis, the hole would still measure accurately, but it would come down through at an angle. Anybody ever put anything together where you try to put a bolt in and one of the holes goes in one direction and the other goes in another direction, it doesn't quite go through. That's because the positional tolerance was not maintained on that. And that positional tolerance meant that this axis that goes right up through the hole, that has to be in not only a particular position, but it has to be within a certain constraint so that the hole is straight enough for something to go down through it. That part makes sense? Positional tolerance is the most common of the tolerances, and it's also the most complex, which is why I'm starting with it. But if you go back to this frame, what the frame is telling you is this. We're going to control the position of whatever this frame is attached to. There's a tolerance zone as opposed to a tolerance range. In dimensions, you have a tolerance range. It's got to be this, no bigger than this, no smaller than this. In dimensional tolerancing, you've got a zone, and I'll show you what that zone looks like in a second. But what that tells you, that diameter symbol tells you, is that the zone in this particular case is circular. It's a cylindrical zone. And what it literally means is we're going to take, and that axis for that hole has to fit entirely inside a straw that has a certain diameter. So if we go to the long one, now here's my long one. If I say this is an extremely large version of a tolerance zone, and I tell you that this has to be inside that straw, it means not only does it have to be inside the straw, but it also has to not go outside at any particular angle. So the positional tolerance on this has a zone that's cylindrical because the axis has to fit into a cylinder. Make sense? The size of that, quite small. In this case, it's 1/1000th of an inch. That's 1/3 the size of a human hair. You take your human hair, pluck it out, or a sheet of paper is about 3/1000th of an inch thick. So it's telling you there's a very tight tolerance on that. Well, why? Because the components are going to be assembled into a nuclear power plant, and you can't have any variation moving around because it might cause a failure of some kind. So a part like that is an expensive part. And the parts, so I have a part that was made in a machine shop, and I was doing some training, and I asked them for a sample, and they gave this to me, and I noticed that it had a red mark on it because it had gotten nicked. And I said, that must be a piece of scrap. And they went, it is. I said, can I have it? They went, well, yeah, it actually came out of a nuclear power plant. That's what it's for. But who knows? I mean, you can't tell looking at it. So they said, yes. The problem is that part right there had a huge amount of money invested in it already. The equipment to make it was expensive. The cost of the people who machined it was high. They got way into the process before they got that nick in there. And so that process of making that cost them a lot of money because the tolerances on this were so small. But that's a small tolerance, and that's the tolerance for position. So you can have a hole that's out of position, but it can't be out of position more than 1/3 of a human hair. Make sense? That 30th of a human hair thing always throws me. I actually have a micrometer that can measure that small. But you have to have very delicate fingers because if you really rank on it, it kind of moves. Now you've got some things called modifiers. And the beauty of this is only true if whatever this refers to is at maximum material condition. I'm going to go back to this. So you'll notice right here, that pocket right there is going to go over something. There's a dimension on the pocket, and the dimension on the pocket is an upper and a lower limit. Up here, it tells you something that's more limited, that's less limiting than positional tolerance. It tells you that the axis of that pocket, that little axis going down through here like that, tells you that has to be perpendicular to something. And the something, when you look down here, is identified as the letter A. That's called a datum letter. And if you take a look at the parts, someplace on that part, there's going to be a little datum triangle that tells you what surface is represented by datum A. You come down here, and that's what a datum surface is identified as. The letter A, that little box with the A in it, and the triangle at the bottom, is called the datum triangle arrowhead, is sitting on another feature control frame, both of which are attached to an extension line, and the extension line extends that surface. So what that is telling the machinist, that's the size you've got to worry about, but also the axis of that pocket has to be 90 degrees to the bottom within, in this case, it's not, the other one I showed you, 0.001 was inches. This is millimeters. So it's 0.08 of a millimeter. That's a relatively tight control. But the idea is if that pocket's not perpendicular and you try to shove it over something, it won't go over the part that it's supposed to go over. Everybody with me on that? Paul.
Yeah, no, so the top feature control. I don't know that's referring to the center axis of that pocket. I always thought it was referring to the surface of the pocket.
Paul just asked an extremely good question, and it all has to do with how that feature control frame is positioned. He said, how do you know that's referring to the axis of the pocket and not the side of the pocket itself? See if I can find a slide in here that's gonna take me a minute to find this one. And Paul, there it is right there. So this is something that came from something I call a pocket guide. And what it tells you is if datums are identified as something, what is it actually controlling? So you look right here. There's a datum right there, datum B, and it's sitting on an extension line. And so, Paul, your question could also refer to how do I know that's this surface and not a center plane that goes between those two lines? Because the location of that control is not lined right up with that dimension. If you look at the other one on the other side, this one right here, you know it's the axis in this case because it is sitting on a line that goes right down through the dimension. So it's being referring to the dimension itself. If it were a surface, you put it right there. In other words, you could attach this thing to that line without having it line up with the dimension line. Now that's pretty subtle. This is exactly the reason I go and do training because people go, I don't get this. Why can't I just call that an axis? Now you might be wondering, what's the difference? The difference is this, an axis has to be simulated using that surface, but that surface itself, depending on the position of the part, can have a characteristic separate from where the axis goes down through. So it's measured a little differently. One's a little easier to measure, in fact. But you've got a few other things like that as well. You got one over here. It's called runout. That runout is attached to the dimension. That means it refers to the runout of the entire, all the way around the entire surface. Give you another example. Do I have a? And again, I'm not going to try to get you too far into the weeds, but here's a very simple example. That's a pin. So there are two ways to identify the straightness of a pin. That's the straightness tolerance, by the way. And that's about as simple, that is as simple as the feature control frame gets. In other words, that pin, say it's this thing right here, it has to be straight because if it's not straight, it's not going to work well. That makes sense to everybody? One of them tells you the surface has to be straight. The other one tells you that the axis has to be straight. So for Paul's question, it's the same thing. The fact that this points to a surface instead of sitting under the dimension tells you that if I put that pin in a fixed location, all I have to do is say the top edge of this has to be straight. If I put it over here, I mean the entire pin itself, the axis of the pin has to be straight. And it's measured a little differently. This one has a tolerance zone that is a cylinder. This one has a tolerance zone that is a sandwich, which means if I drew a line below that surface and another line above that surface, and they were 1,000th of an inch apart, the entire surface has to fit inside that sandwich. Over here, we don't do a sandwich. Instead, we do this. This is the sandwich one. And so here's how you interpret it. You've got a pin, there's a sign, something pointing at it, it gives it a dimension. I'm going to put this on my document camera. So what I'm holding right here is what's called a dial indicator. And a dial indicator, it's a Brown and Sharp, it's an excellent tool company. When you push that in and out, that needle moves. And every time it moves from one mark to another, it's moving 1,000th of an inch. Make sense? Now this one is broken. That's why I have it. The spring doesn't work as well as it should. But normally when you put that against something and then turn it or move it, it'll go back and forth and it'll show you how close something is to being straight. So if I'm putting this on top of a pin and I'm sliding it along the length of the pin, and it's going back and forth a little amount, if I measure that amount and the amount is less than what's specified, that pin is straight enough. And so the way you would use this is you put it down on something and you slide it along, and then you look at the needle going back and forth. And that's how a dial indicator works. So when I say it's a sandwich, those two lines right there, those two phantom lines, they're 0.2 apart, 0.2 millimeters, because that's the straightness tolerance. And all you have to do is run it back and forth along that surface. Then you're done. Make sense? Now the other one is the axis. For the axis to be controlled, then you got to say that's got to go and fit into a hole of a certain size. So this one is using what's known as a dial indicator. This one's what's known as a functional gauge. So someplace in a machine shop, somebody who's really, really good makes these functional gauges. And functional gauges, do I have one with me? I do not. A functional gauge is just something where, so, Grayson and I are working together, and Grayson is our brilliant tool maker, and I'm some bozo on the line trying to figure out if things work. And he says, listen, here's a gauge, stick it in that hole. If it goes in the hole, it works. And I go, oh, that's easy to do. So in this particular case, you make a functional gauge and you say, I'm going to take into account two things. How big can this pin be? It can be as big as 10 millimeters. Tells me that right here. How straight does it have to be? Well, it has to be straight within 0.2 millimeters. That means functionally, that pin has to go into a hole that's 10.2 millimeters in diameter. That's what's known as a fixed size boundary. So Grayson makes me a gauge that has a hole that size, and I put that in there after measuring it, and I say every single place where I measure this is inside that tolerance zone, and it fits through that hole right there. So it's straight enough so it doesn't go outside the tolerance zone on the axis. And it's an axial tolerance zone because if it's crooked, it's the axis that's crooked. Make sense? So it's the position of the tolerance zone. The position of the feature control frame determines whether you're controlling the surface or you're controlling the axis of the surface, and how it's measured differs. And that's one of the reasons you need to know that. Everybody with me on this? Don't you see how exciting this is? Aren't you all dying to take a whole course in this? I actually did teach a whole course in this one time. I had 12 students from the machine tool program that asked me to do an advanced class after mechanical design. And I said, you are the weirdest bunch of people I know. Most engineers don't even like to study this stuff, but we had a really good time. And that's the only time it's ever happened. So, yeah, so that's the idea here is functional. And you think about it. Do you ever put anything together and bolt doesn't fit in there? Anybody ever do that? Just can't get it in. And is it Shirley? Is that how we say that? And what did you do to make it fit? You jammed a drill in there and wiggled it around, and then the part went through, right? Well, you were applying.
Hit it with a bigger hammer.
Oh, well, hammer is similar. We do the similar thing because you made the holes bigger.
I'm kidding.
Well, I'm not kidding, because really you applied geometric dimension and tolerancing, because what you said was that hole is apparently too small, which means it's probably at max material condition. But it doesn't have to be. I can make it least material condition. It'll still work by making the hole bigger. When you make the hole bigger, you're taking advantage of the fact that when the hole is as small as it'll go is the time when it's least likely to work. So now we go back here and I look at this. So max material condition is when the hole is as small as possible. If I try to put that over a pin, in other words, I try to put it over the thing it's supposed to go over, and I've got one here that will not go. I can't get it on there. And I measure this, and it measures 44.45. I'm going to bore it out to 44.5. It's still going to be the right size, and then it's going to go over there. So what I do is move away from maximum material condition to something that still is the right size, still within the tolerance zone. But when I make it bigger, now it's more likely to go together. That all makes sense? That's the fundamental concept right there of geometric dimensioning and tolerancing and max material condition, which is why if you take a look right here, it tells me this zone is fairly small, but it only applies if the hole itself is at maximum material condition. In other words, if I make the hole least material condition, I can make the whole thing crooked, more crooked, by how much more? By the difference between max and min, and max and least. In other words, if the hole gets bigger, now it's going to fit on there even if it's more crooked. So the combination of the sizes and the control and the fact that there's the letter M in here means I don't want to make that hole, that pocket. I don't want to make it as small as it'll go because it's least likely to work then. If I'm a machinist, I'm looking for 44.55 right down the middle because I'm, if I go too close to 44.6 and I miss that a little bit, now I got to throw the part away. If I go too close to 44.45 and it's a little too small, it's not going to fit. Then I have to go back and machine it again. So machinists, when they look at a limit tolerance like this, are always looking down the middle. Go down the middle is the safest place to make something when you make the part. So far, so good. Yeah, I got a few nodding heads here. Yes. Stop me if you have any questions. Answered your question though, right?
Thank you.
You're welcome. All right, so that's this. If I go and look at a few of these other controls, and then we'll come back to positional tolerance. So perpendicularity makes sense, 90 degrees. Up here, we have another one that probably you know what it is already without my telling you. Parallelism. Well, what is that telling me? This is not lined up with a dimension. It's lined up with a surface. That surface goes all the way around the part. And that surface in this particular case is that surface right there. That surface has to be parallel to A. So again, I have to know where A is in order for that to make sense. And if I look at that and then find A is here. And then the question I ask is it possible for those two to be parallel? One of the most common errors that I have in my mechanical design class is people will put a perpendicularity tolerance on a surface that is actually parallel to the surface they're calling out. And what that tells me is they didn't understand what I said in class. If that's going to be parallel, again, it's going to be parallel to within 0.06. In this case, it's like that left pin example where there's no diameter symbol. So this is also a sandwich. So now let's take a look at what the zones look like. This is a slide that I made. Quite proud of this slide. It took me hours to make this slide. And what I wanted to do was to identify every geometric control and show you what every single one of them has as a possible tolerance zone shape. And so I came up with this idea of a sandwich versus a cylinder because some of the controls require a sandwich, some of the controls require a cylinder. If it requires a cylinder, it's because you're controlling the axis of something round. It's either a hole or a pin. So straightness, you saw the straightness thing back and forth like that, right? Well, you take a line and another line, and the distance between them is the number you put right here. That part is straight as long as every single location on that surface falls inside that zone. So when you drag the dial indicator across it, the needle is going to move back and forth from the lowest to the highest point. And if that range of movement is less than the amount put in that feature control frame, that part is straight enough. Straighter doesn't help anything. It can be straighter than that, that's fine, but that doesn't make it better because the idea of a tolerance is anything within that zone is functional enough to work. That makes sense to everybody? So you know how some people are like perfectionists and they over and over and again, they go, that's not quite right. That's not quite right. And you're watching going, the one that is quite right looks just like the one that wasn't, So go ahead if you want to be a perfectionist, but sometimes being a perfectionist is just, you got time that you just, throwing away. Flatness is straightness in all directions. So you think about something like a surface that's going to have another surface on top of it. Those two things have to go together. If the surface is on flat, then they're going to rock. If they rock, then the part's not stable. If the part's not stable, it's not going to work in some situations. So if we go back up here to this illustration, one of the things you always see is that primary datum, that datum right there, that surface, this datum surface, you can't use that to measure any of these other things if it's not flat. So you start by saying that surface has to be flatter than everything else on here, because if it's not flat, you can't measure anything else from it because it does this. That makes sense? So the flatness tolerance just means, listen, we're going to take that dial indicator, Dan's, and we're going to drag it all around that surface. We're going to lock it down. We're going to put this in something, it's a plate that goes on top of a flat piece of granite if it's mechanical. I'll tell you what's happening now. Of course, you don't really use flat pieces of granite as much as we used to. Instead, you use a computer measuring machine or a coordinate measuring machine. This is arm that has a little probe on it, and it's capable of measuring to within the tenth of a thousandth of an inch. And you just take that and you touch it all over, you drag it all around. Then electronically in a computer, it tells you whether or not it's flat enough. But visually, the mechanics of this makes more sense to me. You drop it down, you drag it all around, and make sure that it drags around on something that is itself flat. And granite is used because it's so stable. It's called the surface plate, and machinists love their surface plates. And if you ever get caught putting a coffee cup down on one, you'll get slapped because they protect their surface plate by covering it up all the time. They don't want anything on that surface plate. They don't want anything sticky on there so the part doesn't slide. And God forbid you ever put a hammer on it. You drop a hammer on a surface plate and you're going to get fired. That surface plate was like, that's how you determine what was right. So you have something that's sitting on a surface plate, and then you have a part, and you take the part and you drag this all around the part and you watch the needle. And when the needle goes back and forth, if it doesn't move by more than 2/100ths of a millimeter, that surface is flat enough for its purpose. I saw you look at the clock. Am I over? Oh, okay. So we're still okay. You're probably thinking, is he ever going to show us how to draw this damn thing? We're going to get to that. So that part has to be flatter than everything else. You'll notice that number 0.02 is smaller than all these other numbers because almost everything on here refers back to datum A, because datum A is what's called the primary datum. Now you have three potential datums: primary, secondary, and tertiary, and that's it. And this has to do with what are called degrees of freedom. So if you take any object in space, this thing right here, it has no degrees of freedom controlled. I can put this any place. But if I say, listen, I need to measure it, and if it's moving around, I can't measure it, we need to put it on something. So you think, all right, I'm going to find a surface plate made out of granite. This one's plastic. I'm going to put it on that surface plate. Now, I might not be done because it's still possible for it to do this, and it's possible for it to do that. But what I've done is said, I'm going to control 3 degrees of freedom. When I put it on here, it can no longer move up and down like this. It can no longer turn like that, and it can no longer turn like this. So if you think of the Cartesian coordinate system, there are 3 axes, and around each axis, there are 3 possible revolutions. Those are your 6 degrees of freedom. One's called translation, you moving along an x-axis, moving along a y-axis, moving along a z-axis. The other one is called rotation. You can rotate this around each of those axes, and controlling all 6 of those means that you put this in a position where it can't move at all. Now you can measure it accurately. Make sense? Primary controls 3. Bang, 3 of them controlled. What are the 3 that aren't controlled? 1, 2, 3. It can turn around the z-axis. It can move along the x. It can move along the y. It can't move along the z-axis because it's sitting on that plate. It can't rotate around x or y because it's sitting on that plate. That's called the primary datum, and the primary datum can be established with 3 points of contact. And in fact, if you put something down that doesn't rock, it's sitting on the 3 highest points of whatever you put it on. They're so small you couldn't see them. It's not like you're looking and seeing little bumps, but there's always surface irregularities. And what does it do? The 3 highest points of contact are the ones that control it. When I started teaching, I'd ask this question, and about a quarter of the people in the room would say yes. Has anyone ever milked a cow besides me? If you ever did, you had a stool you sat on, and the tie-up, which is where you keep the cow, the floor is always beat up. You take a nice chair with 4 legs in there and set it down, and it's going to do this every single time. So what's the milking stool got? 3 legs. What's your tripod have when you take a photograph? 3 legs. Why? Because 3 points of contact is stable. You do that, now that can't rock. That's why when you don't have something that can fit all together on a surface plate, it might be a little too big. You go over here where you have these datum targets. So we're going to look on this side now. Over here, we've got these dots. And, oh, wait a minute. I'm going to start SolidWorks, and I'm going to open up something and show you. So I've got these little dots right here. You all know what a phantom line is, correct? Yes? Phantom line? the line representing something that isn't actually there. Well, those little circles, hang on while I just started a piece of software that doesn't let me move it out of the way until, here we go. So you look at that circle, a little hard to tell on here, but that circle is actually drawn with a phantom line because there's nothing there. It's a location that doesn't have a physical characteristic. It's got section lines drawn on it, and then it's got a hidden line pointing to it, and then it's got a datum target identifier, and it's got a diameter, and it's got a letter A and a number. The reason for that is this. If for some reason I don't have a surface plate that I can set that on, I have to have that sitting on 3 points of contact. So we go back to Grayson, my tool maker. He makes me another gauge like that that has those 3 little pins. You see those pins on there? Can you see them okay or not? So there's 3 pins here. Well, if I take this and I put it over this and I line it up so that those 3 spots that are identified in the drawing are sitting on those pins, now those 3 pins prevent it from rocking. That would be my primary datum. So why do we, that's the one I wanted. Sure, this is the one you got to work from. So that's a phantom line. Actually, that probably looks more like a phantom line. You see that little double break, little gap right here. So what it's saying is that that point or that area, that datum target, and that datum target all add up to datum A, which means they can be used to simulate the flatness of that surface as long as the pins themselves are flat. And that's a case where you have a place in a machine shop that can make better parts than the parts you're making. And that goes back to the idea that if that surface isn't flat enough, there's no point in measuring everything else from it. If I give you tooling to hold something and the tooling to hold something isn't more accurate than the thing I'm holding, then the thing I'm holding can't be controlled. So if I give you something that clamps and the whole clamp is able to do this, and then I try to put a hole that's really accurate in the thing that's being clamped, it's not going to be accurate because the holding device, the fixture, is not accurate itself. So there's something called a tool room, and a tool room machinist is somebody who works in tolerances that are usually 1/10 tolerances required for the part itself. So if I'm making a part that's going to go, piston that's going to go into an engine, and I say the tolerances on that piston are plus or minus 10 thousandths of an inch, which is pretty big, that means I better build tooling that's plus or minus 1/10 of that amount, which is a thousandth of an inch. More likely, the piston's going to have plus or minus a thousandth of an inch, and that means I better be able to work in plus or minus tenths of a thousandth of an inch. So that's because the tooling you make has to be more accurate than the parts that's being made. Tool room machinists make more money than regular machinists. And, my father was a tool maker. I was a machinist, never was a tool maker. And I would have had to be there a lot longer in order to become a tool maker. So that's what these things are. Now there's also, and this is just, you don't need to remember this, that's a hidden line. So when you draw it, just make sure you duplicate what's here. The reason that's a hidden line is we're looking at this on the right view. So if you look at the front view of this thing, the front view of this thing is that. Actually, how does that look to you? To me, it looks like it's going off to the right. I guess from your point of view, the front of this is that. But anyway, you got this thing oriented a certain way. And then if you look at the right side view is here. Well, where are those targets? Those targets are on the back side. If the targets are on the back side, you have to identify them with a hidden line because they're hidden. If I had a view like that, I would not have a hidden line, but otherwise it would look exactly the same. So the point of that is that's why you have to understand the language of technical graphics in order to interpret things accurately, in order to make drawings that are accurate. Anybody have any questions right now? Is there anything you're thinking, man, he just said something that's just puzzling or confusing? Or are you with me on this so far? So far? What I want is for you to understand the concepts. I don't necessarily want you to think I can apply these. You're going to duplicate that drawing. And one of the reasons is so you can understand the tools built into AutoCAD to make that a little easier. There are better programs than AutoCAD for creating mechanical drawings, but AutoCAD is the most widely used CAD program in the world, which means it gets used to do this kind of stuff all the time. So do I think SolidWorks is better than AutoCAD for this? Absolutely. If I already own AutoCAD and spent $4,000 and I don't need to buy SolidWorks for another $4,000 or $5,000, can I make an AutoCAD drawing that does what I need? Absolutely. So this class bases on AutoCAD because it's such a widely used software program. And the various disciplines we cover are covering things that AutoCAD gets used for. But in some cases, there are better programs to use this than what we're using here. And in my opinion, the better program is this one, which is SolidWorks. They already did a SolidWorks project, didn't they?
Nice.
You haven't done it yet? Okay. So I'm just going to open something up, and I'm going to open something up that will be really familiar to you. And it is this. It's going to be like a magic trick. This. In other words, that's a 3D model of that part you're looking at. And I just put basically little stickers on the back. There's nothing actually there. I just put some circles and colored them in to show you what that would look like. So that's the reason that those are there, is so that they would match up with the pins on a device that you're using to measure it. Everybody with me on that one? So the first thing you do when you're trying to measure anything is you first establish a primary datum that keeps everything from rocking. Now you need a secondary datum to keep it from moving around. Well, if I did this could move around like that. Everybody see that okay? But you notice this little tooling I have here that's got this kind of boss in the middle. That boss is this center hole. That's my secondary datum because the primary is those pins. So this has to sit on the pins. And then that pin in the middle expands so that can't move back and forth, which means I've now got 5 degrees of freedom that have been constrained. The only one left is this. That might not matter. And in this case, it doesn't, because this is completely symmetrical. It doesn't have a keyway in it. There's nothing on it that would index it. So it doesn't matter where this goes, as long as when I turn it, it's sitting on those pins in the right place. So 5 degrees of freedom, then this part can be measured. 5 more minutes to a break. When do you take a break? Okay. All right. Well, you forget. Yeah, I do that all the time. Today I said, hey, you guys forgot to tell me to take a break. And somebody goes, well, you were talking. We didn't want to be impolite. I said, I was talking? That's shocking. Normally I stand up here and mute. Oh, I knew where I was going with this. So now we look over here, and you notice over here, there is another datum identifier here. And the other datum identifier is a letter C. And what it's doing is telling me that that little pocket right there is a datum as well. Now, I don't know how it's going to be used. It's not necessarily, even though it's the letter C, it's not necessarily a tertiary datum. A tertiary datum would be the third datum that would stop this thing from turning. That doesn't do it. So it's probably going to be a secondary datum. There is another datum, but that other datum is used independently of that. And the other datum is B, and that's that hole that goes through here like this. But check out over here. Over here, I've got a positional tolerance, and that positional tolerance is controlling the holes and the hole pattern that is used to bolt this to something. And you'll notice it's identifying 2 datums. The first datum it identifies as the primary datum. 3 points of contact, has to control rocking. That's where I start. The second datum is the secondary datum. In this case, it's the letter C. So in the case of this, the secondary datum is that pin in the middle that keeps it from sliding this way and sliding that way. If I really wanted to index it, I could identify something else on here as a tertiary datum and then say it has to line up with something. So for instance, if there were a keyway that went through here and it had to go on a shaft in a particular position because it was like a cam of some kind, so it always had to be in that position, then the keyway would be a slot going through, and that keyway would become my tertiary datum, and that would completely control the movement of this thing, completely control it. Otherwise, in many parts like this, I control it by saying, what's my most important surface? That one. There's my primary datum. What's my next most important surface? Let's just say one of the sides. Now, once I've done that, all it can do is back and forth. Now I can add a tertiary datum here, which means if I have three mutually perpendicular surfaces, I just set that in there and now it can't move. That means every time I measure it, I'm measuring the same thing. As opposed to some days I measure it like this, some days I measure it like that, because when you do that, it changes the measurements. And so you can't be consistent about how you determine if something is going to work. So primary, secondary, and tertiary, 3 points of contact, 2 points of contact, 1 point of contact. If you ever see a drawing with 4 datums referred to in that frame, the person has no idea what they're doing. And I mean, no idea what they're doing. There's no such thing as a 4th datum. There's nothing left to control. Primary is 3, secondary is 2, tertiary is 1. That adds up to 6. That's it. There's nothing left. So take a break right now. All right, we're going to take a break for 10 minutes or so. And then I'm going to find out from Paul if I'm doing what he wanted me to do. All right.
Here's the best part.
Now it's all done. So it's in the first bath. Hey, folks, I'm back. The time, yeah. How's everybody doing? Does this make some sense? Grayson, makes sense? Yeah. Quan, Kristen, Luke, Shirley.
Yes, sir.
Again, there's a lot to this, so it's not as though you're not necessarily going to be an expert at it. I wouldn't put it on my resume yet if I were you. I'd give it like a couple more minutes until I get done. But what I really want to do today, and what Paul wanted me to do, was to have you look at this and say, I don't have any idea what's going on. Now you have an idea what's going on. What I want to do now is go through some of the other controls here. And I want to then talk a little bit about this positional tolerance over here. Then we'll go and open up AutoCAD. We'll take a look and see how you would go about laying this out. Paul is going to show you how to make some dynamic blocks, I think, that are going to be helpful. Okay. All right. All right. So what I'll do is I'll cover the way I would lay this out. And by the way, somebody the other day wrote me an email. I watched your video and I watched Paul's video. You don't do this exactly the same way. And I go, no, we don't. That's absolutely true. The procedure might change. When we get done, they're both right. So, I sometimes do it one class and the next class I do it differently. And the people will watch both recordings and go, wait a minute, you did it differently the next class. And I go, it doesn't matter if I put the peanut butter on first or the jelly, I'm still going to end up with a peanut butter and jelly sandwich, right? So, Bill Belichick one time did a video on making a peanut butter sandwich. And you know what his big revelation was? You put peanut butter on both pieces of bread so that the jelly doesn't seep out through either one of them. And I thought, that was a really smart move. So anyway. Okay, so let's talk about.
Wouldn't that make the top to be red and the bottom to be yellow?
Yeah. You know how you make a peanut butter sandwich and all the jelly kind of oozes out and you're like, my hands are all sticky. I don't really eat peanut butter sandwiches, but I know Paul does, so he's going to start making them that way. So, okay, so listen. So what are these other things? Perpendicularity, that's pretty clear. That thing has to be perpendicular to a surface, says the surface. Parallelism, same thing. That surface has to be parallel to A. Position we'll come back to, but then we have this thing right here, which is really interesting. This is called runout. And runout is essentially a vibration control. If you've ever ridden a bicycle where the front wheel was a little bit warped, little bit potato chip, and you're driving and it kind of does this and you put the brakes on and they do that, you're experiencing excessive runout. And runout just means the extent to which that wheel moves back and forth as it's turning. Now you can get runout on something like this as well. If this is spinning and I put a dial indicator right here, and as it's spinning, the needle goes back and forth, that means this is now not symmetrical about its axis of rotation. So that's what runout is. On a mechanical part, if you have excessive runout and it turns really fast, it creates a huge amount of vibration. That vibration then causes failure. If you've got, say, the rotors on your brakes on your car, which is this disc that goes through between 2 brake pads, and those brake pads squeeze down on the rotor. If you've ever had a situation where you take it in, because when you put your foot on the brake, it does this a little bit, grabs, let's go, grabs, let's go. And they say, oh, we got to turn your rotors. That means the rotors are now warped and they're experiencing run out. They go back and forth as they turn. So that's run out. And run out's the easiest one to measure. You just put something, you control it by attaching it to whatever spins it. And then you turn it slowly by hand and you run this thing back and forth and see how much movement is going to be in that needle. The more movement there is, the more run out there is. There's run out and there's total run out. So flatness, we looked at straightness. Run out means I put my needle, my dial indicator at any given point and measure run out. And if it falls inside, everything's fine. I pick it up, I put it to some other spot and I turn it. And that means if it's not in that range, it's fine. Over here, do the same thing, but I don't compare them to each other. So run out is at a particular location. Total run out means I turn this thing, and as I turn it, I move back and forth. So the total run out, sometimes known as total indicator run out, TIR, the total run out takes into account the entire length. So it's interesting because in a sense, you're not directly measuring straightness, but what you're doing is taking into account straightness and run out. As a result, at this every point along the way, you might have a specific run out, but if you total them up, the actual amount that it varies is higher. So total run out goes the entire length. When something's long, if you I mean, if you take a look at this, I mean, you could have put total run out in this as well. And it's funny because it seems to me total run out is always going to be a more useful. But what you do is normally see it as something's relatively short. If you have a long, like a drive shaft on a vehicle, you know, the drive shaft that go on a pickup truck that goes from the engine back to the rear axle, that's really long. You put that someplace and start spinning it. The total run out really matters on that because when you're driving along, so, you know, one of the shops I worked in, we used to actually straighten drive shafts, you know, with hydraulic press, so that they wouldn't have that kind of run out. That's always interesting too, because you have to over bend it in order to straighten it. You know, if it's something's like this, you have to bend it past the straight point. So when it comes back, it comes out straight. And you're using a hydraulic press that if something comes out of it, it comes out like a bullet. It's just really a mess. So let's just now, I'm going to go and just show you all of the controls. And there's all the controls right here. So those are the symbols. So one control is straightness, and that's just one straight line. One control is flatness, and that's a sort of a rhombus. Now there's circularity, the extent to which something is actually a circle. And by the way, that doesn't have an axis. You make a sandwich, and that sandwich is two circles that are concentric, and the surface has to be between those two circles that are concentric. Cylindricity, which is fun to say, there's a symbol, and that just means circularity is, again, at one point. Cylindricity is along the whole cylinder. Profile of a line, though, and profile of a surface, which are getting used more and more. These, to me, you could eliminate straightness. You could eliminate flatness. You could eliminate, well, to some extent, circularity, because profile of a line just means no matter what the shape of that line is, you're controlling it. It doesn't have to be straight. Straightness is like a special case. Profile of a surface would be like this. We don't have profile of a surface on here. But what's happening more and more often is people are saying, you know, what if we just said every part of this, that whole surface has to be that profile right there. So we're just going to offset that profile and make sure that every point on that surface falls inside that irregular profile. The problem with that is you're usually over tolerancing something because you're saying, you know, it's really critical here, not so critical here. But if you use a profile, which is an easy thing to put on a print, it's just a hard thing to actually hit. But profile is so useful if it's used correctly that there's this whole category of controls to show what you mean when you call something out as a profile. So this, I always love talking about this, but you don't want to hear about it right now. Oh no, this is not the right one. I don't have the right. Yeah, I pulled this off the R drive. I've expanded this since I had on the R drive. So never mind what I just said. I take it all back. Okay, so let's go back and see what the symbols look like again. And then angularity. Now, angularity by itself should control everything, but angularity is a separate control from perpendicularity and parallelism. They're actually all angularity. One's 90 and one's 0. So you could get rid of perpendicularity and parallelism. In my opinion, if I was setting this up, I would dump 4 of these things and just allow others that are already there to take a new count. So an angularity is something like this. If you got a part that looks like that, and I tell you that part's 30 degrees, okay, 30 degrees is fine, but the angularity controls the extent to which it falls inside a sandwich where the 2 slices of bread are exactly 30 degrees. So the measurement of this is you take a plane and another plane, and every part of that surface has to fall inside that sandwich. The sandwich is 30 degrees. In order for that to be true, the sandwich has to be called out as what's called a basic dimension. And this is one of those things where people go, basic dimension is a perfect dimension, theoretically perfect. How can that be? There's no such thing. Well, there is such thing. There's such a thing. I'll be right back. My little beeper went off. Rachel is in the industrial design class, and what's that? And I'm printing, or was, and I'm printing something for them on my 3D printer, and it has to be washed in alcohol for 10 minutes. And if you leave it too long, it's bad. And then it has to be washed again for 10 minutes. I'm going to be back for just a second. And well, I know it's not going to hurt. I'll be right back. All right, 10 minutes from now, I'm going to do the same thing. So, but now I'm back. Oh, here's some good news. Concentricity, so difficult to control, so difficult to measure. They eliminated it in the latest standard. Symmetry almost also was eliminated because those two were used. The people applied them all the time, but they're very hard to measure. And they are better ways to measure what you're really trying to control. So those 2 things have been removed. Circular runout's 1 arrow, total runout is 2 arrows on this now. So if we go back to this, what I want to do now is just talk about something that is a little bit confusing, and that is the whole idea of a basic dimension. And I'm going to start by talking about this control right up here, which is a positional tolerance control. Now, again, the positional tolerance control in this case, it's cylindrical. That means we've got this very tiny cylinder. That cylinder starts out being perfectly straight, and the axis of the hole has to fit inside that cylinder like that. It can be like this, it can be like that, as long as it fits inside, and the cylinder itself is the same length as the thickness of the part. Well, never mind, I was going to tell you unless something, but anyway, it's the thickness of the part. So that hole right there has a control on it, but you notice there's something called a composite positional tolerance frame. There are 2 frames here. One of them controls the entire pattern. And that means if I've got a pattern, a hole pattern, that's those 6 holes there, and I need to bolt that to something, the pattern itself has a location. The entire pattern can move around. If I bolt it to something, it's going to probably have studs. It's going to have 6 studs that come out. Those studs can move around as a pattern, and they can move around a fair amount and still work, because as long as all the holes themselves are spaced the same way that the other holes are spaced, everything lines up, even though the part might be moved slightly as a whole part. So what you have here is this. The top one controls the location of the pattern, and that's controlled by determining an axis common to all the holes. And you say that whenever the holes are made at maximum material condition, that pattern has to be fairly tightly controlled in terms of its position relative to datum A, that surface, and datum C, this one. And that's only true at max material conditions. So we go back to Charlie and her hammer, or Cheryl Lee and her hammer. If you make the holes a little bigger, the pattern can move even more. That all makes sense? So you put your drill in there and wiggle it around, you're going away from max material condition. However, if within that pattern, two of those holes are too close together, doesn't matter where the pattern is, it's not going to fit because the holes are too close together. So this composite positional tolerance frame controls the position of the whole pattern, and then a tighter control the individual holes within the pattern. So each of those individual holes can move around that much inside the pattern. The entire pattern can move around a little more. The number at the top is always bigger than the number at the bottom. There's another case where I've seen drawings before when I've been done training. Those two numbers are reversed. I go, whoever put this on here doesn't know what they're doing. So don't follow this drawing. No, go back. What I'd say is go back and ask for clarification because someone made a mistake. Maybe it was a typo, maybe whatever. The problem with all this stuff, there's actually a word for this or a phrase called decorating drawings. Engineers get almost no training in this when they're in school. In fact, I've had students come down, mechanical design students from Orono, and they'll take a mechanical design class down here because they don't understand this stuff. The problem is they think they should. And so here's what they do. They decorate the drawing with this stuff and put really small numbers in there, i.e. expensive numbers in there. So it's a terrible way to design, but it happens enough that there is in the industry, in the trade, there's a phrase for it, decorating drawings. It's almost like, hey, my Christmas tree needs lights. My drawing needs geometric controls. Let's throw some on there. And here's what they'll often do. They'll look at a drawing like this and they'll say, well, that's a thread. I'll put that on my thread. And the next thing you know, you've got controls that are almost impossible to meet or are really, really expensive. But this is the concept of a basic dimension. You can't have two separate tolerances controlling the same thing. The composite frame controls not the same thing. One controls the pattern, the other controls the holes inside the pattern. But you cannot also have a tolerance on the dimension that locates the starting point for those holes. So that's a positional tolerance. If you take a look, what controls where those holes are? Well, you've got a hole pattern here, and there's a bolt hole circle right here. If you follow it along and find what the diameter is of that circle, it's right here, and it's 84. It's not 84.2 to 85.5. It's a box around the number 84. That is a basic dimension. If you put a tolerance there, now I'm going as a machinist, wait a minute, I've got a positional tolerance and I've got a starting point tolerance, and now you get stuff that's it's impossible to do. So the concept of a basic dimension is this. All of this is assuming that you're starting at a very specific theoretical location. That means that the person in the tool room, I had Grayson in my tool room. I don't know if Grayson's even a machinist, but anyway, you're now a tool maker until the end of class. He can make things as good as possible. And that essentially says, as good as possible, make me one of these that controls that dimension. Now, all the variation allowed in position is contained right here. There is no tolerance on that dimension. Nor is there a tolerance on this one, which controls the location of those datum targets. It's got to be as close as 74 as possible to make. Make sense? And that's known as a tool room tolerance. And sometimes you see a box around something because what you're saying is get Grayson to make it and tell him it's got to be as good as he can do it. I mean, it's a weird thing on a drawing because you cannot put a tolerance on a box dimension, on a basic dimension. But you have to have tolerances on every other dimension. You take a tolerance like over here, if that was 44.45 with a box around it, it means as close as you can make it with the best equipment, the best machinist that you have. Down here, we have the angle between those holes, also a basic dimension, because that angle would also cause it to move for two different reasons. If you put a dimensional angle here that had a tolerance associated with it, then that angle could change as well. But you don't want the angle to change. You want to say, I'm going to start with a theoretically perfect location for every single one of those holes and for the entire pattern. And then any variation permitted so that it does in fact have a tolerance will be geometric and not dimensional. That all makes sense? So when you see, because I know the first time I saw basic dimension and I read that it was a theoretically perfect dimension, I go, what does that mean? I mean, what's theoretically perfect mean? I'm actually making a part. I'm drilling a hole. No, there's no concept of a basic geometric dimension. So Paul's question was this: can you just put flatness with no number and mean as flat as you can make it? And the answer is no. You have to have a number in there. Now, what you do is you put a number in there that's small enough and manageable. But the fact is, the geometric controls themselves are controlling whatever feature they're associated with. So you can't also provide a tolerance that is dimensional. Now, this shows up on, do I have a drawing of that? Well, it shows up if I did a drawing of this, because I tell you that's 30 degrees, but that 30 degrees would be in a box. Perfectly 30 degrees. What's the variation permitted? There's a sandwich that's 30 degrees. So I got my two pieces of bread and I can somehow make them exactly 30 degrees. And the space between the two slices of bread is whatever number I put in the tolerance for angularity. Now, if the entire surface fits between those two surfaces, everything's fine. This is a far more logical control than having an angular tolerance. And the reason is, so I have that slide here. Well, I just tell you, you got an angle, right? So you're off by half a degree. The further away you get from the apex of that angle, the further off you are. So if you get an angularity control, the length of the surface determines what you're actually controlling, which means you don't really know what you're controlling. Whereas if you say, no, 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 that surface has to be 30 degrees within that sandwich, the theoretical sandwich is 30 degrees because the tooling you made hold it at 30 degrees. Now you find out by dragging, you do the same thing. You basically set it up so that you now have this at an angle that you can control. You drag it all over the surface. And as long as the surface doesn't extend beyond that sandwich, its tolerance is close enough. 10 more minutes. I'll be right back. So, so Rachel, I'm just letting it dry now. And once it's dry, we put it in the oven. I mean, yeah, so you know, and then you can pick it up there. It's going to take a while for it to go through, but you can pick it up anytime, so you'll have it for tomorrow night. So we have 3D printers here, and right now I hate them all because, well, 2 of them are working. I had 5 of them working, and then one of them stopped. It's just one of those things that it's very, very useful. I mean, I wouldn't have this without a 3D printer. I didn't make that out of soap. But one of them is a resin-based printer, and it's a really, really good printer. And I got 2 of them. And so it uses laser light to harden a photopolymer. And so it's extremely fine and continuous. You don't have little layers, you know, nothing comes through them. When at the beginning of COVID, when the respiratory therapy department at Maine Medical Center approached me and said, we have a plan that we could use to put more than one person on a ventilator. We've got all the equipment we need, but we don't have a fitting that would allow us to connect them. The one thing I tried printing it something for them on regular printers. None of them held air, but this thing here, perfect, and was perfect right off the bat. So what I'm doing now is dipping it in alcohol. It washed all the excess resin off, and now it's got to sit and dry, and then we can put it in another device that really hardens it up, and then she'll have an access to it. All right, so the idea with this is that, and I don't have what I was thinking of before. The idea of this is that's what all the things that you're looking at here, that's what they all mean. Now, there are a couple of things we haven't talked about, but I think I've talked about everything that you need to understand. Any questions about that? Anything I missed? Folks at home? This is pretty involved. Most things are a lot simpler than this. Many things are a lot simpler than this. Positional tolerance, though, is really common, and flatness is really common, although that could be a profile control too. If you put a profile control on that and said it's a surface, it's flat, it's going to mean exactly the same thing as that flatness tolerance. Profile controls give you a little bit of an advantage, but the thing about a profile control is it actually lets you determine the direction the sandwich goes. Flatness just means you make a sandwich, and we don't care where the sandwich is, it's around that surface, and as long as the surface falls inside it. Profile control says starting from perfection, you can only go this way, or you can only go this way, or you can go this way, either one. But you can't do that with any other control. So you're going to see profile if you're in this field, you're going to start seeing profile more and more often. The other thing you're going to see more and more often, which I think everyone should do, and this is one of those things where I have to do some convincing when I do training, but people always agree when I finally show them the reason. This number right here, or even let's go down and look at the straightness. Let's go down and look at straightness tolerance again, because that's so easy to visualize. Um, I forgot what I was about to tell you. This is the problem with having an old guy doing this. Oh, I think I know. Um, no, I did. I had an idea. That was something I wanted to talk to you about.
Back to the other slide, see where you came from.
This one.
So you were there.
I said profile goes one way or the other, blah, 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 blah.
You got the line, you might not use flatness.
All right, I'm gonna come back to that.
You talk about why you might use a profile control as opposed to flatness.
Right.
They show you better on that one. Is it-
I know, but there's no flatness there, it's straightness instead. But that could be profile of a line. Okay. Yes, let's go down. All right. I think I know where I was going now. I know that's never happened to any of you, but you have to give me a little bit of allowance for being a little older than most of you. All right. So listen, we could have put profile of a line. That's that little curve like that instead of just the straightness. And what that would mean is this. Normally, if I put nothing else, it means starting from right here, we can go up half of that and down half of that. But it's possible with profile to say, no, you can't go any lower than that. The entire straightness tolerance is going to have to be away from the part. So there's a technique for doing that, and it's known as a differential, oh, I can't remember the phrase now, but in other words, it tells you it's not equally distant. You can either go out by a certain amount or in by a certain amount. You don't need to know about that. So let's put this over here and let's go down and look at the drawing itself. Did I start AutoCAD? I did not. Oh, you don't have an icon for AutoCAD. How do you not have an icon for AutoCAD on your taskbar? I'm bawling Paul out because because he didn't do it exactly the way I do.
Okay, folks, Dan just got done the smart person stuff. I'm going to show you an approach, or at least the approach I would take to draw this. And just like Dan, I haven't drawn this thing in, well, since last semester, so I don't draw it all that much. So I'll have to poke a little bit here, but let's do this. I'm going to start a new drawing. You guys just start with your template. I'll just start with ACAD ISO here. Next Tuesday in class, we'll talk about dimensioning this and some dynamic block stuff and stuff like that. But right now, you should just kind of focus on drawing it. And I'm going to XREF in. I'll XREF in that PDF. So I'm going to bring in the PDF here. And downloads, I'm going to assume. Okay. All right. And let's scale this thing, get it relatively close. So you can say scale, pick right here as the base point, R for reference, I'm going to say from here to here is 100. Okay. So a couple of things in the process I would do. I tend to have a construction layer. I also have a tracing layer. I guess those could technically both be. Obviously, you'll need object layer and all that stuff. I'm not doing that part, but I guess maybe I can at least do. Let's do object, and I'll do trace, which will eventually become my object lines, and I'll just do construction here. So let me make maybe the construction yellow, and I will make the trace red. Let's go with red here. And for now, I can just here. Right? So what I would let's go back. Let's just go to let's make the construction layer current for a minute. All right. So what I'm going to do eventually is I'm going to draw the right side. So I'll draw my circles, and then right from there I'm going to draw my construction lines over. Right? You can kind of see I want to draw construction lines that go through these major. Right now I'm just hitting on the actual object lines, right? So we've got a object line here. This one is that M42, so it's a diameter of 42. There's a metric thread designation. All right, so I can have that one. Now, it would also help to have this here, which is so in that case, we want this to be maximum material conditions, right? So what's that going to be? Well, in this case, we would want this to be the biggest number possible to be maximum material conditions, right? Because if we push that up this way or push it this way, we end up having more material. So that should be 36, right? So we want to come over for, let's come over for that one. Oop, no. That's going to be a hidden line. So that'll be that hidden line. It'll be this hidden line right here. Right, so that'll end up being, oops, I wanted to do array again. So that'll end up being this hidden line right. Nope, I did that twice. Right, it would end up being that one right there. Right. So, and then lastly, what would we need? Well, we're going to need the diameter of what, 31.8. Again, for this one, we would want that outer diameter to be the biggest. If we have a hole for maximum material condition, we want that hole to be the smallest, right? It leaves the most material behind. So I guess one more time we could say ray, and I could bring that ray over. So if I just wanted to start tracing the outside of this, right, I would be pretty good to go, right? Now, well, let's come over, and now let's draw some of this, right? So I'll just track over here. And it doesn't matter if I'm lined up with this or not, but again, I would kind of start. I would start on the right side, and I'd start drawing my circles. Right? So we have a diameter. The outer one is going to be 100, right? We want that to be the biggest, right? All right. So now, if we want this surface here, we could jump down, and now we need this circle here, right? And what that is going to be is, again, in that case, we would want this to be the bigger of the values, right? So the bigger this size is, the more material we would have, right? And that's for this right here. We come around, that's the 57.6, right? So we could do circle, come right here, 57, diameter first, and then 57.6. Did I get that right? I don't know if I did. I didn't. Let's go to properties. I fat fingered it. Diameter 57.6 is what we were looking for, right? Cool. All right. So as we start to come down, we've got those first two. Right? As we come down now, we're going to need this, and that's going to be that diameter of 42, right? So we can add that circle. I won't do the whole thing. I'm going to spend a few minutes here. All right. So we've got that one. The next come down, we would have this inset here, and if we trace over there, right, now we're going to need this hidden line, right? And to get that value, we're going to come right over here, and again, in this case, we want the bigger value, right? So the more material, the bigger this value, the more material we would leave behind. So that we want a diameter of 36. It's a tricky drawing to do, folks, but it's a good one. Once you're done, you kind of feel pretty cool about the fact that you did it right. And you might not do it right the first time, trust me. And then what was the last one we wanted was going to be here. And again, that's going to be the bigger. So we want a diameter of 31.8, right? So we could say circle. One more time, diameter 31.8. Okay, cool. All right, now let's just do maybe an X line or something. So I'll do X line. I can track. Yeah, let me put on quadrant O snap. So we can do X line. I'm going to hover from the quadrant. I'm going to track, and I'll just come over, I don't know, maybe 60 units or so. Well, millimeters in this case, right? And I have this edge right here. All right, now, let's, Dan talked about this, but again, we're drawing everything to maximum material conditions, right? So if we have an overall size, we want the bigger value, right? The more material that we would have. But if we have a hole or a slot or something, we want the smaller value, so we take out the least material possible. The other idea is, this is at maximum material conditions is where the part is least likely to work, right? Because we're making everything, or the holes, is all as small as possible. So this offset is going to be what? 41.3, right? So I do my offset 41.3. And I'm going to bring this, and I'll offset that over. Now, if you want, you can clean this up. The other thing I might do here is... let's put an X line, and we can just run an X line right through here. And maybe let's, while we're here, let's create a center layer. We'll put that on a, oops, I don't know why I did that. Let's do sen, and I'll call this sen line, just to differentiate between my sen marks, which I usually leave as continuous. Let's load, and we'll do CEN, load up center 2. We'll grab center 2. Okay, we'll choose OK. Cool. And we can just leave that as yellow, I guess is fine. Let's put that on the center line. Okay, so there's our center. And eventually, all we have to do is draw everything above the center line, right? And again, you can see we're kind of shifted a little bit from the image, but that's fine. Okay, so let's do this. Let's go ahead and just clean up, I guess. I always like to have kind of a bounding box to start with. And again, I'm not going to draw the bottom, but let's still have the bounding box, right? Think of a bounding box. If you had to make a box for this front view to sit in, it would now fit in that box right there, right? It's the right height, and it's the right width. So now you can just start offsetting. Right? So if we kind of come over here and offset these values, and again, Dan mentioned, right, you want the smallest for each of these. If I offset this, the smaller value, 9.4, I'll leave the most material behind, right? So offset 9.4. I'll bring this in, right? Spacebar gets me out, spacebar gets me in. I'm going to offset, what, 25.4. So 25.4, I'll grab that, I'll bring that, spacebar out, spacebar gets me back in. I'm going to offset, again, the smaller value is going to be 35. And we can offset that. Cool. And that gets me to this edge right here. So, cool. Now, I do have another offset, and the other offset is for this inside. But I'm going to hold off, and that's that value here. Now, what's that going to be? Well, again, if I go to the smaller value here, I would end up leaving more material. So I'm going to want that to be 9.2. But let's not worry about that so much right now. All right, now, if you want, you could also have a second construction layer. Maybe you want, a different color coming the other way. So that might even help. So if we come here and we say, hey, I want, CON1 or something. And make that some other color. Maybe that'll be helpful, right? So we could make that maybe green or something. Okay. So now I'll just start bringing over some rays here. Oops. I don't know what I typed. I don't even know what that command was. I should have looked a second because I'm not really sure what it was. But I'm going to bring these over. All right. Cool. Nice. And now what I end up having here is I kind of have the intersecting points that I need. Let's do this. Let's just so it doesn't make a mess over here. Let's get rid of them over there so they don't go all the way over. And well, I mean, I guess I could leave those there if that kind of helps, right? Because now you can kind of see where we're going, right? So we've got a line. I'm going to come over to the first offset that we have. And again, it's not really the first offset, but I skipped this one. So we're going to come over, and we're going to come down, and we're going to come down to that first intersection, right? So I will switch to my trace, and you might even want to put line weights on at this point so it kind of stands out. And you might want to crank up, so I could go to trace and maybe just crank the thickness up. Might make life easier. And if we go to our line weights, let's go to line weight, and we can pop the line weights on. Right. Cool. Okay. So as we kind of look at this, now we have what? Polyline, and the first one's going to come from here to here, right? Then we're coming down to here. Then I know we have to come out to that next, right here. Then we're going to come down. We have to come down to here. Now, did I forget offset? I did. So we would also now need this offset. So I have to offset this distance. And again, I'm going to offset this line right here, but I would want to offset that the smaller value, right? So if I offset that 6, again, it'll leave the most material. So offset 6 units. And I would have needed to offset that. And if we go back to polyline, now we're here, right? So at this point, you know, I've just drawn that section, right? Now I need to come back up, and I'm going to come back up to the 42, but that's not the right. I look like I should have gone down a little bit. Oh yeah. This should have gone down more. I stopped at the 42, my bad. So let's get rid of that. This should have come down to here. Then P line, right? This would come over to here, and then I would come up to that point, right? So now we're at that point, and again, now I can just kind of keep coming over, and it just, to me, it just kind of makes things a little bit easier in my head to draw this, right? Now we're coming all the way down to there. And then eventually I'm going to come out to here, and then this is going to come down. But I don't have that. I don't have that 20 circle drawn. So I could have. Well, did I draw it? I didn't. Right. So I could have said circle, and that's going to be the smaller, right? So diameter of 20. L enter. All right. And I guess I should have stuck with my colors here, so we can put that here. Stick this on here would make more sense, right? L enter, and now this is coming down to here, right? Now I cannot finish this though, because I need that spot over here where I stop, right? So what I could do is come back here, and now I can offset, and if I look here, I'm going to offset this, the smaller value, right? So 9.2. So now we could come here and say offset 9.2, grab this, bring that back, and now that's where this is continuing to, right? Which would be to there, right? So now we're at that point right there at that edge, right? So now we just need to come up, and to come up we have to have this circle drawn now. So we have to have that, and again that's going to be a smaller, right? So 44.45. You know, at this point, if you're like, hey, all right, things are just getting a little hectic, I don't need this anymore, maybe let's get rid of that, right? So whatever works best for you. But we can say circle, diameter 44.45, I think it was. L enter, and I can just bring that over as a line, I guess, for now. And again, make life easier if you put these on some other layer. I'll just put them both on that yellow layer. Kind of keep with my method. I'll go with here. So now that's going to come up and then all the way back out, right? So I could say L enter. Right, I'm going to come from here. That's going to come up to here. It's going to go back to there, and now I've got that shape that eventually I'm going to revolve. Now you've got fillets and things to do here. But eventually, well, you're not going to revolve. It's not 3D class, but you could, right? I mean, you know, if for those of you in 3D class also, and some of you are, you know, if I joined all those together, oops, Dan's point about the trim command. Sometimes it can be a little bit of a pain. But if I now revolved all of that around my center line, unable to revolve the selected. I probably have some lines that overlap themselves, I would assume. A way to solve that problem would be this. Yeah, let me do this. Let me get rid of, let's get rid of all that stuff. Let's get rid of this stuff here now. And I could do, what, -BO? I could click inside, say enter REV, L for last, and my revolution point is going to be here. Enter. And the reason that wouldn't revolve is because I probably had multiple lines on top of each other when I joined. But anyway, you know, again, this isn't perfect here because we don't have the, you know, fillets and everything in that we should. But you can kind of see we get to the point where we have our part, right? Okay, so let me undo a little bit. And then for you, once you get all your fillets and everything in, it's just going to be a matter of, you know, you can mirror this down now through the center. And you'll have, you know, some other stuff to do here, right? You're going to have some lines that have to continue through and what have you. So, but that should hopefully get you to where you need to go. All right, good luck.